Good afternoon, ladies and gentlemen. Thank you very much for the opportunity to present to you again. Last year I presented sensor sorting for evaluating drill core. This time I would like to follow up with a presentation on an actual ore sorting plant at McCreedy West Mine in Canada. So as an introduction, currently a big topic is the clean energy transition, which we are currently all facing, and that there's an increasing demand for critical minerals, and amongst these is nickel and copper, and this is what this mine is about. At the same time, the industry faces increasing pressure on improving the growing sustainability targets as well as the ESG policies. Therefore, it is also necessary to develop new possibilities to address these demands, and sensor sorting can provide some of the solution. So this presentation is about a copper nickel ore which is extracted at McCreedy West Mine, and all the ore that is mined needs to be transported to a local concentrator, which is about a 90-kilometer round trip. As an introduction, multi-sensor sorting, which Steinert prides itself in having developed considerably over the last years, and I'll show you some of that later. And so in this paper, I just want to show you how we developed this project from its initial testing methodology, and then the next stages, and at the end I'll show you some of the plant and some photos. So as an introduction as well, KGHM are the owners of McCreedy West Mine. They are a large company based out of Poland, and they have significant copper production sites all over the world. McCreedy West Mine is on the northwestern limb of the Sudbury Basin. There's a nice picture of it shown in that slide. And as an introduction for the Steinert multi-sensor sorting technology, which we pride ourselves in, we have up to 4 sensors which we can incorporate into one sorting machine. In this case, we will only utilize 2 sensors, the laser and the X-ray transmission sensor. But for many applications, we can also incorporate up to 4 sensors in one application, fine-tuning the sorting efficiencies. So to be able to successfully sort ore, a heterogeneous ore body is essential. If you have an homogeneous ore body, it is nearly impossible to separate good rocks from bad rocks. So, and this picture is taken from an underground workings at McCreedy West Mine, which clearly shows how you have a vein of nicely dense sulfides, and you cannot just mine this vein. You will definitely have dilution from both the hanging and the footwall and sidewalls. Also, this picture also highlights the diversity of the mineral deposit. You have different zones. They are mining copper-rich zones, and then they also have nickel-rich zones. And some zones also, I think, with the nickel, they also have platinum, gold, and other precious metals. Again, a nice picture of the heterogeneity of this ore body. You can see the stringers, and you can see lots of internal waste dilution as well. The next thing which dilutes the ore with waste is the way you mine. If you have longwall mines, you will always get contamination. So to what extent can we separate this? So when we do evaluate these ore bodies, we get the geologist, with the help of the geologist, we define the different types of ore we have, say the high grade, massive sulfides, disseminated sulfides, and the different waste rock types. We scan those, we define, we teach the machine basically what these types of rock look like in our teach tools. And from there we start developing the sorting algorithms which eventually will help us separate the different types of rocks into different grades. So we start off with a scoping study. The main sensor which is most important is the X-ray transmission sensor. So in other words, we are radiating X-ray energy through the particle, and we have two different sensors picking up pixel by pixel data of each rock. And as the picture shows, let me just get my... We do have the X-ray generator generating X-ray through the particle onto two sensors, the high-level channel and the low-level channel, giving us millimeter by millimeter pixel size data points which show the absorption levels of each pixel. And these get plotted on a scatter plot like this, where the high energy gets plotted against the low energy, and you can clearly define the area of the dense sulfides, for instance, in this case, and the waste rock. And once you have that, we can develop a sorting algorithm giving us a classified image, and you can then define at what stage do you have high density pixels, and at what stage do you have low density pixels, and based on that you can then define how much % of red pixel do you want to put into your product or your waste. The other thing which we utilize in this case is we utilize a laser. The laser gives us a profile of each and every particle, and from that we can then also use the X-ray absorption values. The highest X-ray, the highest absorption would be down here. If you had a piece of lead which is totally absorbs all the X-ray energy, would plot down here. And along this axis we have the height of the particles, say in millimeters. So your large particles down here and your smaller particles down here. And so you would have an X-ray absorption value per particle height, and it's even more accurate than the previous slide showed. So in our scoping study, we use a cascading type of methodology to test the ore. So the run of mine, once we've defined the sorting program, we put a typical sample of run of mine through the sorter. We set different sensitivity settings. In this case, in the first sensitivity setting will produce the highest possible grade, and then we take the rest of the material, change the setting to get the medium grades, and so on and so forth, until we have a final product. What this then gives us is a grade recovery curve like this, where we can plot, say, the copper and the nickel values. And in this case, we did a reverse sort. So you see that in the first stage, we got, at different stages, we can get high-grade ore. We doubled the grade in, say, the fourth step, with a mass recovery of 51.9% and a nickel recovery, nickel and copper recovery of about 97%. So, and anywhere along these points between these steps, the sorter can actually be operated at. We follow this. This was a small sample of about 50 kilos. This gets followed up by numerous other large bulk samples before the client actually then decided to purchase this machine. And the bulk test also showed really good results. In this case, you can see the grade recovery curve. You can, in the first step, we could increase the grade from 1.9% copper to a product of 4.21%. And in the final step, it was 1.9 and the product of 2.3% copper at various mass recoveries. In this case, we chose the step 3 setting, which gave us a product of 2.67%, a mass recovery of 66%. Basically, a third of the material can be rejected as waste, and you still get a very good nickel and copper recovery. Here are some pictures of the sorting plant. Let me just go back. So you can see it's in Canada. It gets pretty cold up in Sudbury. Therefore, the plant had to be designed so it can and needed to be heated. The first building you see, the white canvas building, is the screening building where the material gets prepped, and the right size being fed into the sorting plant, which is the blue building on the right. What is important as well in this application is to clean the surfaces. Lots of high-grade fines are clinging to each and every particle. That's why we have a washing screen. And the wash water actually is cascading down into the mine to the first level, where it gets settled out, and the fines look something like this on the right-hand side of the picture. High grade, which can go directly into the smelter in this case. This is the pan feeder to the sorter. The pan feeder's objective is to separate the material into a single layer, so that we can have the particles separate when they are on the 2.8 meter per second belt speed of the sorter. Going through the sensors. Important is also the compressed air station. You need a decent sized compressor as well as an air receiver close to the machine, so that you always have enough air when you separate the particles. After all this, here's some operating data from the day-to-day running of this equipment. We're running at a feed size of -38 plus 19 millimeter. The throughput is about 40 to 50 tons per hour. We reject about 40% as a product. In other words, we are rejecting 60% as waste. Incidentally, the waste is being sold to the surrounding mines as aggregate for the underground roadway construction, and the waste income they generate from that actually pays for their operating costs. The feed grade varies. Typically, it's about 1% copper. The waste grade is about 0.15 to 0.3, and the product is typically almost double from what we get as a feed. And the recovery of the copper is between 90 and 95%. In summary, the McCreedy West sorter has a few important points which I'd like to highlight. The ore sorter provides to McCreedy West mine the ability to have additional run-of-mine available from lower grade zones. In that, we were able to, and they were able to expand the reserve base, and in that, the life of mine. There's a tremendous energy cost reduction, like mass has been reduced, the waste removal reduces the mass, reducing the transport cost, reducing the mass mill feed, and we only feed higher grades into the mill, reducing, also has a big environmental impact. I consider the ore sorter like a valve to this mine, in that you can control the grade you are going to feed to the mill, and you can produce a consistent grade to the mill, and the ability to also change the sorting parameters depending on the changing conditions. The waste grot, I mentioned it earlier on, the waste is used as aggregate. Right, I conclude this by thanking Mr. Dave Truscott from KGHM, who helped me put together this presentation. Thank you very much.